Today we're going to take a look at aqueous solutions part 5. In our last PowerPoint, we looked at balancing redox reactions as if they were typical chemical reactions. Sometimes this will work. However, sometimes we may not know all of the parts of the reaction and we'll need to figure that out. In order to do that, the first step is to identify the half reaction of the oxidized substance and the half reaction of the reduced substance. By this, I mean to figure out which substance is oxidized and write the reaction of those substances only, and then to do the same thing with the reduced substance. Once we've done that, we will balance out each of those half reactions, excluding hydrogen and oxygen, using coefficients like we would in any other reaction. Then we would add hydrogen ions or H+ ions to balance out the hydrogens and water to balance out the electrons. Lastly, we would add electrons to balance the charges. Then we would multiply our reactions to achieve equal numbers of electrons, cross off all substances that appear on both sides of the equation, and finally combine. We'll see an example of this on the next slide. In the example you see here, the first step was to identify my oxidation states. The first one, my chlorine, or Cl2, is easy. It's a pure element, and therefore it has an oxidation state of 0. My Cl-1 is a monatomic ion, and therefore its charge is equal to its oxidation state. Chromium +3 is another example of a monatomic ion, therefore its charge is its oxidation state. Here, oxygen is a -2. There are 7 of them, giving us a total of -14. We know the overall charge for this is a -2. Therefore, together, all of my chromium atoms must equal a +12. There are 2 of them, so each one of these is a +6. The next step is to identify which reactions are oxidized and which are reduced. If we take a look at the chlorine, it goes from a -1 to 0. This means that it's lost electrons. Remembering, Leo, the lion, says grr, losing electrons means you're oxidized. So the first step in this problem is to write the oxidized reaction. The original oxidized reaction looks something like this. The reason this is the oxidized half reaction is because I took only the substances that are involved with chlorine and wrote them in one reaction. For the reduced reaction, I would take all elements that include chromium and write them in a half reaction. So these are my 2 half reactions. Per the rules in the last slide, the first thing we would do is balance our atoms. If I have 2 chlorines on the right, I have to have 2 on the left, hence this coefficient. There are no hydrogens nor oxygens in this oxidized reaction, and therefore it's not important that we balance them. However, it is important to balance the charge. At this point, this right or the left-hand side of this equation has a -2 charge because there are 2 chlorines that each carry a -1 charge. To balance this out, we're going to add 2 electrons to the right side. This is now a balanced half reaction. For the reduced half reaction, the first thing we want to do is balance chromium by throwing in a 2. Then you'll notice we have 7 oxygens on the left-hand side, so we need 7 oxygens on the right. That's where this 7H2O comes into play. By adding 7 waters, you have added 7 oxygens to this reaction. However, you've also added 14 hydrogens. So to balance that out, we're going to add H+ ions. The hard part now is figuring out the charge. On the left-hand side, we have positive 14 for our hydrogens here, plus a -2 for our chromates. That's a total of positive 12. On the right-hand side, I have positive 6. So to make them equal, I'm going to add 6 electrons. 6 electrons plus a positive 12 equals a positive 6. Now both sides of the equation are equal. The last step is to ensure that we have equal numbers of electrons in the oxidized and the reduced reactions. To do that, I'm going to multiply everything by 3. As you can see below, that gives you 6 chloride ions, 3 chlorine molecules, and 6 electrons. Our chromate or reduced reaction is the same. Lastly, we're going to cancel out these electrons because they show up on both sides and combine the overall reaction. That's what you see below. If a redox reaction specifically states that we have an acidic solution, we're going to use these H+ ions to balance out the hydrogens. If we're specifically told that we have a basic solution, instead of water, we're going to use hydroxide ions to balance out the oxygens. A redox reaction in a basic solution is very, very rare. This is a more likely situation. So we're going to look at the first example here, balancing the following reaction in an acidic solution. First things first, let's identify the oxidation states. Tin plus 2 has an oxidation state of positive 2. It's a monatomic ion. Manganese plus 2 is a monatomic ion and therefore has a charge of positive 2. And tin plus 4 is a monatomic ion, so it has a positive 4 charge. In my MnO4-, I have a -2 charge for my oxygen. Given that there are 4 of them, that is a total of -8. The compound itself has a -1 charge, therefore manganese here must be a +7. So let's first identify what is reduced and what is oxidized. Oxidized means that we lose electrons and become more positive. In this case, tin has gone from a +2 to a +4, which must indicate that it has lost electrons. So that is my oxidized substance. Given that I've told you that we're going to be losing electrons, safe bet those electrons are going to show up on the product side. The tins are balanced and there is no hydrogen or oxygen, so let's look at the +2 and the +4 charge. These need to be equal. I can't add any more positive charge to the left-hand side, but I can add negative charge to the right-hand side. In doing so, +4 minus 2 is +2. My charges are now balanced. My reduced substance is my manganese. We go from a +7 to a +2, which implies we've gained electrons and are therefore reduced. So I'm going to write this one out again. And now it's time to balance. My manganese ions are good. They're 1 and 1 on either side. My oxygens are the problem. I have 4 on the left and therefore need 4 on the right. So let's go ahead and add 4 waters. This balances my oxygen problem. My hydrogens, however, are not balanced. At this point, I have 4 H2s, which is a total of 8 hydrogens. Given that this is in an acidic solution, I'm going to be adding H+ ions. I've added 8 H+ ions to balance out my overall hydrogens. If I add up my charges on the right-hand side, there's only a +2 coming from my Mn. On the left-hand side, I have a positive 8 minus 1, which is a positive 7. Well, if I add 5 electrons to this side, I get minus 5 plus 8 minus 1. That equals positive 2. Right now, my charges are balanced. The last step is to guarantee that my electrons balance out. The only way to do this is to multiply the top by 5 and the bottom by 2. This will give me 10 electrons in both reactions, which will allow me to cross them out. My overall balanced equation then is 5Sn plus 2 plus 16 H pluses plus 2 MnO4s. This produces 5 Sn plus 4s plus 2 Mn plus 2s plus 8 waters. And now I have a balanced chemical reaction. Let's take a look at an example. First, we're asked to find the oxidation number of uranium in this compound. We know my oxygens are -2, so I have a -2 times 2 is a -4. Uranium here must be a +6. In part C, we are asked to balance this equation given that we are in acidic solution. So we already found the oxidation states of these. Let's take a look at the others. My oxygens will be -2 across the board. This makes this nitrogen a +2. This uranium here must be a +4, and this here gives me a -6, so this nitrogen must be a +5. Let's see what we've got. My nitrogens are going from a +5 to a +2. This implies that they are gaining electrons and are being reduced. My uranium is going from a +4 to a +6, implying that it's lost electrons and is oxidized. So, let's break it up. There's my oxidation half reaction. And there's my reduction half reaction. So looking at both of these, my uranium and my oxidation reaction is completely balanced. My oxygens are the problem. I have 2 oxygens on the right and only 1 on the left. So let's go ahead and add some water here. Now to balance out my hydrogens, given that I'm in an acidic solution, I have 2 H pluses on the right. This is now, in terms of the atoms, balanced. Let's look at our charges. On the left-hand side, I have a +2. On the right, I have a total of +4. So let's add 2 electrons to this in order to get a neutral or an equal charge. In my reduction reaction, I have 3 oxygens on the left, 1 on the right. So let's go ahead and add 2 waters in over here. I need to then add 4 H pluses on this side. Now let's look at our charges. On the right-hand side, there is no charge. On the left-hand side, I have +4 minus 1, which is +7. So I need to add 7 electrons here in order to make this work out. Now that I have all of my charges and my atoms balanced, let's go ahead and make those electrons equal. I'm going to need to multiply the top by 7 and the bottom by 2. The hard part now comes with looking at my hydrogens and my oxygens. So I'm going to rewrite it above, distributing my multiplier. I have 7 waters plus 7 UO plus 2. I have 7 UO2 plus 2 plus 14 H pluses plus 14 electrons. In the second reaction, I have 14 electrons plus 8 H pluses plus 2 NO3 minus 1. Then I have 2 NOs and 4 waters. Easy ones are my electrons. They're equal on both sides. We made that point. Here I have 8 H pluses on the left and 14 on the right. So 14 minus 8, this becomes 6. I have 7 waters on the left, 4 on the right. So my 7 here becomes a 3. Combining my reactions, our final answer, 3 H2Os plus 7 UO plus 2 plus 2 NO3 minus 1 produces 7 UO2 plus 2 plus 6 H pluses plus 2 NOs. This is our final reaction.